Log on, tune in, find out. Another good idea from Cambridge.
Go ahead, talk.
Okay. First of all, I would like to thank organizers of this workshop for their awesome job in bringing so many people together, in providing such a wonderful workshop, in giving us so much time for coffee break and tea breaks, because I think that it's very beneficial because we can talk to each other, and I think that coffee breaks sometimes are more important than talks themselves. Although I want to say that I enjoyed each talk, and they helped me to look outside the box, because personally I learned a lot from this workshop, and I can see probably further applications of mathematics, further applications of what other people are doing, and again, I'm so pleased that I have been invited to this workshop, and I have been given a possibility to talk. Again, thank you for all organizers. You see, my work has provided in collaboration with Dr. Hritonenko from Houston and Dr. Prairie. He's a wonderful collaborator because he accepts what I call him. Yes, he's a very nice person. And he is from Center of Operations Research and Econometrics from University Catholic de Louvain, from a very, very beautiful small city and the youngest city in Brussels, in Belgium, called Louvain-la-Neuve. And if you have not visited this city, you should go. It's a great city. In our workshop, we talked about how to predict climate changes, right? What to expect from climate change? What expectations should we make? But in my talk, I will go away from this. We will not try to expect what happens. We'll talk about how much and what to do with this how much if we are given less than we expected. And what to do if we already have this climate change, how to deal with negative impacts of climate change. Now, first of all, according to IPCC, and this document has been mentioned several times during our workshop, a few strategies to deal with climate change are mitigation and adaptation to global warming or to climate change. Mitigation or abatement is just some methods to reduce the sources of greenhouse gases or enhance the sinks. And adaptation to climate change is some adjustment of some adjustments in natural and human systems in response to negative impacts of climate change. And here, again, and it's very important to discuss interrelation between these two strategies. And if you take a look at the last issue of The Economist, we see that 2 papers are devoted exactly to these issues. I think more than 10 pages in this small journal. And what can we say about adaptation? We have to adapt to climate change because you see we have to live here. If we do not adapt, then definitely we have to die. And what measures of adaptation can we make? First of all, here again, I can talk a little bit about this, but it's from my collaborator, exactly this Dr. Prairie. And I don't want to provide some misconception, but I will, if you don't mind, I will explain to you how I understand it. It means mitigation is everything, it's the net emission. Abatement is just a little bit smaller gross emission. But again, I am so sorry that I could not answer your your question in full, but if you ask me about mathematics, don't worry, I will answer all questions, because I did mathematics. Yes, now adaptation. How can we adapt to negative impacts of climate change? Even positive. First of all, temperature becomes hotter, warmer, and therefore we have to modify crops, to probably introduce new crops, and then that will survive this hot weather. What else can we do? We can introduce dams in order to keep water. We can probably develop new lakes. Let's say if you look at the map of Texas, you will find a lot of lakes, and you may think that this state is full of lakes, but only one lake is natural. The rest of lakes are artificial. The population in Arizona increased very, very fast after air conditions were invented. It means people were able to adapt to severe climate of Arizona, and they moved to Arizona, but they needed air conditions or adapt to this climate change. Now, also we can talk about some other implementations, but also we don't have to forget about limitations of adaptation. And we can talk about different types of limitations. And I just want to emphasize your attention on environmental, economic, social, informational, financial, and so on. Let's say even limitation. I think that everybody watched TV today in the morning or yesterday and so on, and you know what is happening in Scotland right now. People are sleeping on the road for more than 3 days. They cannot move. Why? Because you see, this part is not or does not have adaptation procedures. They don't have evacuation routes. What happens if we try to adapt to this climate change? Let's say we have to think about evacuation. We have to think about how to inform people. What happened in Houston a few years ago when we had Rita. More people died during evacuation than from the hurricane itself. And not a little bit more, several times more died during evacuation. Also, we have financial limitations. And what can I say about financial limitations? According to the World Bank of 2009, just adapting to 2 degrees by 2050 will cost approximately 100 billion US dollars. Where can we get this money? But we are talking about developed countries. What can we say about developing countries? According to a different study, we need 68 billion US dollars to as adaptation costs in developing countries. And also, how can we estimate how much we need for adaptation? It's another very big question. Then if we get some funds for adaptation, where should we invest this money? Let's say to what sides of adaptation this money should be invested. There are a lot of different questions. But you understand that even if we adapt ourselves to negative impacts of climate change, you see, actually, we have to do something else. Because adaptation is not enough. We need to provide some measures and invest to abatement. And let us talk about abatement. What measures can be given to mitigation and abatement? First of all, we have to provide quotas or develop quotas. We have to develop alternative energy sources. We have to deal with carbon sequestration. We have to deal with a lot of problems in forestry. And we can use geoengineering methods. urban planning, government and non-government approaches. And definitely we have to work in all directions. By the way, according to some sources, we can say that carbon sequestration, then problems of forestry and geoengineering sometimes are considered as alternative tools to mitigation, or it means they are considered separately. And at the end of our talk, if you have a little bit of time, I will talk about carbon sequestration and some problems in forestry. Now, the goals of our study is just to develop a mathematical model that helps us to understand how to deal with abatement and adaptation and abatement, where to invest money. Also, we want to provide some mathematical justification of balance between adaptation and abatement. We want to understand how the stage of development of a country or depend on abatement and adaptation, or it would be better to say in a different way, how adaptation and abatement depend on the stage of the country. And in order to do this, we started to work on the model, 3 of us together. First of all, we considered a one-country case, or a closed economy. Then we considered a very famous SALUS one-sector macroeconomic growth framework. And then we considered a Cobb-Douglas technology with a constant return to produce final good Y. You see, it's a production equation, where A and alpha are parameters of Cobb-Douglas production function. And what can we say? A alpha is the share of capital in production. A is the level of technology. And actually A, this parameter, shows us what country we have. If A is high, then we have a well-developed country. If A is high and small impatient factor rho, but we'll talk about rho in one slide. If A is small, then we have a developing country, and we'll use it later on in our research. Also, we introduced the distribution equation. It's Y equals this one. The social planner assigns Y across the investment into physical capital, investment into adaptation, abatement, and capital. These are law of motion of physical capital and adaptation capital. And here we can see their dependence on deterioration of, for physical capital and for adaptation capital. And we can see that, let's say, adaptation increases with the investment into adaptation, and adaptation decreases because of depreciation or deterioration. Then we consider the following objective function. Here we have the utility function, and what can we say? This rho is the rate of time preference. P is the pollution intensity, and pollution is important in our research. And the next slide is devoted to the description of pollution. What we did, what is the novelty of this objective function and of our model is consideration of the adaptation. It means I don't know any models that consider adaptation and abatement at the same time, or when adaptation is involved in the objective function. Also, you see, we take the utility function, or U, to be additively separatable. And here we are not the first one. There are a lot of other papers, and I just presented a few of them, where U is taken as a sum of several parameters. And you can see our case that we have considered. And here we involve logarithmic function, but I think that we already had several talks where objective function considers logarithm of some values. Now, this factor is very important. It will be among the key factors of our model, and it presents the environmental vulnerability of the economy to climate change. If adaptation increases, then this factor decreases. If adaptation is 0, then this factor will be very, very big. And therefore, we can talk about this factor as the efficiency of adaptation measures. Also, 1 plus mu, this one, 1 plus mu, where mu reflects the negative increase in marginal utility of pollution. You understand that here we take 1 plus mu in the denominator because of the future first derivative, because we want just to have a little bit easier equations. Now, pollution. Pollution is a very important component of our model, and it shows the quality of the environment. And there are different equations for pollution. Pollution can be considered as a stock, it can be considered as a flow. In some papers, it's considered as a stock and a flow. We decided to consider pollution as a stock. You can see the first derivative, or it's given as the ODE, where gamma is another important factor that shows this gamma is called the emission impact factor, or the environmental dirtiness to produce a single good. If gamma increases, then definitely P increases. It's understandable. The more we produce, the more we pollute. But what can decrease some pollution? Abatement measures. It's B, and therefore B is in the denominator. Now, delta P is the coefficient of natural decay of our pollution. And if it increases, then P will decrease. Now, let us just talk about, let us summarize our model that we are going just to investigate. First of all, it's a macroeconomic model. This type of models is used a lot on research, but what is new? The new is the mix of adaptation and abatement investment considered by this model. What else is new? That the utility includes the environmental impact and depends on adaptation expense. And the rest, let's say, Cobb-Douglas production function can be found in other models. Now, how we investigate this model? Now we go to the part that I know perfectly. But you see, first of all, we considered a I don't want to say a very, very simple model, because it was challenged to investigate this model, but compared to what we did next, it's a very easy model, because you see, we just considered this model without any adaptation. And then we considered this model with adaptation and abatement and compared results, because our goal is to understand the importance of abatement and how can we correlate, or what can we do with abatement and adaptation together. Then we determine interior optimal solution. We found a steady state in this case, and we showed that our solution will converge to this steady state. And we investigated qualitative properties of model parameters. Now, during our study, because again, I looked at this clock and I understand that I have to go faster, you know that when Mark Twain was asked how much time he needed to present, he answered, if I know the stuff, then I need approximately 10-15 minutes. If I know the stuff a little bit, then I need probably 1 hour. If I don't know anything, then I can talk and talk and talk. You understand what case you have, because we have started this research. We introduced a parameter kappa that presents the indicator of environmental pressure. And I will go a little bit faster because I want to show our conclusions. And from investigation of our problem without adaptation, we probably had some feelings that this factor would play a very important role, and we were correct. Then we also considered a special case for the environmental vulnerability. I told you that this parameter would play a very important role, and we considered this in this way. You understand, when adaptation is 0, this parameter would take its highest value. If adaptation approaches 0, then this parameter that is responsible for dirtiness will be small. When we investigated our problem, we found out that the marginal efficiency of adaptation also would be very important. And actually, it will take a critical values. It will have some critical values that will be important to our study. Then we analyzed the same problem with adaptation. And again, we found the steady state equilibrium. We also showed a very good convergence of our solution, optimal solution, to the steady state, and we provide static analysis. Among them, we found out that there is a value of capital for which adaptation is not important at all. It means adaptation is 0. I am sure that you want to have some mathematical proof, right? And I am going to show this proof because, again, it's what I did. Please. Yeah. Now, also we found another value, and this value is our m. I told you that you would see this m, right? And this m, what provides a value, and if our adaptation efficiency is less than this value, is less than this value, then again we don't need to provide an adaptation. It means if you have money, then it would be better to invest them into abatement. But if m is greater than this critical value, then adaptation is crucial. Again, if you're, please. Yeah, I see that 5 minutes, and therefore, if you're interested in this, it would be my pleasure just to talk about our results, because they are interesting. But again, I have just 5 minutes. Also, in some special case, we found the solution to the problem. And we could not solve this problem in general, but in some special case under these assumptions. And in order to show that these assumptions are real, we provided model calibration on realistic data. It means we took several countries of different stage, and we found out that these assumptions are realistic. And we found a solution to this problem. Then we investigated this solution, and we found very interesting results. Now, we investigated not only the solution, we also investigated different ratios. Especially, you see, we were surprised with our results on that ratio. It's the ratio between adaptation and abatement and capital. Here, the first conclusion just tells us that we have to, the investment into abatement should be proportional to capital. It means if you produce something, then you have to invest the portion of consumption to the abatement. And it does not depend on the development of the country. But in this case, you see, when we considered the ratio between adaptation and abatement, we found out the inverted U-shaped result. Also, we can, again, I just wanted to show you our results. First of all, we found out that abatement and adaptation are imperfect substitutes, and they have the inverted U-shape. It's here. What does it mean, inverted U-shaped? In our case, that if we have a poor country, then probably this country should not invest into adaptation because no money. If the country is rich, very rich, then again its investment into adaptation is sufficiently much smaller than its investment into abatement. And if the country is in its middle state of development, then it would be wise to invest into adaptation. Here we just contradict or challenge results of some other researchers. We also provided data calibration and model simulation. What are we going to do in the future? First of all, we want to extend our results to N countries, to N country model, because as you understand, we consider a closed economy. It means we don't have any influence from the abroad. Here we want to consider some relations between different countries. And actually, I think that we'll get very good results because mathematics is ready for this case. Also, we want to add technological change. And here you see, I am looking forward to adding technological change because results can be different and can be more optimistic. Why? Because you see, new equipment is less, you understand that it's better, it pollutes less, it's more advanced, and it is better to use new equipment. And actually, but here we have to introduce integral or PDEs, and I have very good background in technological change, and I think that results will be very, very interesting. But it's again, it's our next stage. And also I want to show you another model. It's again a model related to carbon sequestration in forestry, where we consider net benefits, where net benefits is the objective function, and it includes benefits from timber production, from carbon sequestration in soil and biomass, minus expenses to plant new trees. And here we introduce effects of climate change. This model has been approbated on real data. It means even this one, and we compared qualitative results and quantitative results. And you see the difference between our qualitative results and quantitative results that used in forest in Spain is just 0.6 centimeters. I think that it's a very good correspondence. And we hope that our further research in this area will be also beneficial. I provided this research with my collaborators from Spain. And again, if you're interested in this model, you're welcome to talk. And we have published a few papers on carbon sequestration. And because it's my time, I would like to thank you for your attention. Thank you very much.
Could your one country model apply to the global economy?
Yes, actually, when we took, when we provided model calibration, we actually, it was challenge, but we sometimes even we considered as a global economy, as you said. Sometimes we considered some countries, developing, developed, and so on. And the results were for all countries that we considered.
Have you considered the implications of uncertainty in your analysis, and have you included the investment in climate science as one of the...
You see, we did not consider any stochastic in this model, because you see, the model also is the ODE problem, and it's the only ODE problem that I'm working on, because you see, I work on nonlinear integral models and PDE models. And I thought that the investigation of this model would be very, very easy. Actually, we met a lot of challenges, and therefore, if we invested some stochastic, then please understand the investigation would become very, very challenging. And second, whether we considered investment to
climate science, because that must have a feedback on...
Yes, we are going to consider this in the future. Probably if we consider technological change, then we'll consider investment into research and development. And then we will consider investment into climate change science and some other development, and investment into some other development measures. Please. Sorry. Yeah, please.
Yeah, I think these models are really important because they're essentially a loss function. So they're sort of the other end of the decision problem. But maybe I missed it, but I didn't see where climate went into the model, where sort of temperature might go in, or
In what model? In the first or
in your model. So
in the first or second model? In second model, I can tell you. Look at this. Here you have the function g, this one.
Yeah.
It's a growth. And here the function g will depend on climate change. And you see, when Tim presented, Dr. Palmer presented, he showed different scenario. And we have considered scenario A2 and B2. And then we tried to find out how our system will act, or would act, depending on these different climate scenarios. Because then all parameters, let's say, in this case, all parameters would be different. And we considered this dependence, and we already submitted 2 papers, and another paper is on the way. Because again, although probably the main technique is the same, but some other challenges have been added to the model investigation.
John, you have a question. I think we'll have to leave it after that. John.
So, John Rusha, so this U-shaped response is
Inverted.
Inverted is unintuitive and potentially very interesting. But you only achieved it in a static analysis through making some very strong practical choices at the top of your model. So the question I have is, how do you demonstrate the robustness of this response function in situations where more realistic choices at the top of the model would lead to a tractable analysis of the static?
You see, actually, we are thinking about this. It's a very good question. It's a very good question, an excellent question. We are thinking about this, and we are working about this. But we showed very good convergence of our solution to the steady state. It converges very, very fast. It means not during the unlimited period of time, but on a very good time period. But robustness, again, we are thinking about this. Robustness, then dependence on initial conditions, on initial situations, is for our future investigation, because we have just started to work on the first model. We just have ADP paper. It means only in Cora. We are working on this model right now.
Okay, thank you very much again.
Okay, thank you.